Okay, so I guess most of you have already started with your labs. Just let your UPIs or TAs know if you're facing any problem with the lab one. I know that for some of you the components have not arrived or they are going to arrive later this week or early next week. If that is the case, just let your UPIs know so that they are aware of the situation. We understand that this is the first lab, and of course, by the time of the first lab, it is possible that some of your components may not arrive. So we'll take care of that those situations on a case-by-case basis. But for that, just let your EPIs and lab TAs know if you're facing any difficulty with the components. And I know someone also mentioned that their DAD board did not arrive in time, and they are only about to do the first part of lab one. But for most of you, I guess you already have a DAD board, so which means that you should be able to carry out most of the experiments for lab number one. And also the video had been posted from last year's EPI meet number one, where I think the last year CPI mentioned how to solve these lab one problems. So please go through that if you haven't gone through the videos yet, and if you have your labs pending next week. Now, for today's lecture, we are going to discuss a few more loop gain examples, but keep in mind that these examples, I'll probably go through one or two, which should get you started on how to analyze some of these loop gain based examples, but rest of it will be self-study. So there are a few, like 3 or 4 pages of examples. Just go through them to understand more or to practice more about how to solve these loop gain problems. And then we'll start with our op-amps intro. We have effectively already started our discussions on op-amp, but we looked into one specific configuration, which is called a non-inverting amplifier configuration. We'll look into other configurations that are possible with op-amps. For these analysis, we'll just take a look at, or we'll just analyze the A infinity. That, okay, assuming an ideal op-amp, what is the gain you should expect in those different configurations? But then again, you can always go back and do the loop gain based analysis if you want to know what happens when the op-amp is non-ideal. Okay. But then again, the approach for the analysis will be mentioned, whatever is the configuration. All right. So with that, again, let's get started with the examples that we have in the self-study document that I have posted for lecture number 7. So as you see, this first one, so it's again, you have an op-amp, you have some kind of a configuration over here where you are applying this input. You're applying this input to the inverting terminal of the op-amp. So as you know that the op-amp will basically have a non-inverting terminal and an inverting terminal and an output. So it's a 3-terminal device. And what your output is basically the gain times the difference between the positive terminal and the negative terminal. That's what the output of an op-amp is in an open loop scenario, right? But and that's what gain means. That okay, you have a input between these 2 terminals. Your output will be the gain of the op-amp times the difference of the 2 outputs. But whenever you have the op-amp in these configurations where you see that there are these additional resistances and there could be, let's say, for example, capacitances or inductances as well, if you just want to make the circuit more complex. But in this course, we'll mostly deal with resistances. So don't worry about those more complex configurations. But what it really does is that it introduces some kind of a feedback from, let's say, output to the input. And in presence of the feedback, you want to analyze the overall circuit. So what's the first step to do that? You try to figure out what is A infinity, or what is the gain of the circuit, assuming that the op-amp is ideal, which means you have infinite input impedance, 0 output impedance, and infinite gain. Now, infinite gain only means that the gain of this block is infinite. It does not mean the gain of the entire circuit is infinite, because the circuit has a feedback. And you know that with negative feedback, the gain reduces. That's the theory of feedback. So what would be the reduced amount of gain with the configuration that you see here, that you can analyze using, let's say, either KCL or KVL or the feedback analysis, whichever method works for you better. So right now, the way we are solving this problem is doing a nodal analysis. So for example, to find out A infinity, you know that the current that is going into the positive terminal is 0, the current that is going into the negative terminal is 0. Why is that? Because the op-amp has an infinite input impedance. Because the impedance is infinite or the resistance is infinite, you can have no current going into the op-amp. Which is another way of saying that because of the infinite impedance between the two, and because there is no current between the two terminals, the voltage at the two terminals will also be equal. And that's basically saying that you have your virtual input, or in some cases it's also called virtual ground. So just assume that if this positive terminal were connected to ground, then we would have called this negative terminal a virtual ground, because virtually there should not be any current flowing in between these two terminals because of the infinite input impedance property. So if one terminal is grounded, the other terminal has to be grounded, right? And that's why, like in an AC sense, that's why it's called the virtual ground property. Now, if you do not have one terminal connected to ground, what will happen is that the voltage at this terminal and the voltage at the other terminal will be equal. Again, why? Just imagine this very simplified scenario that you have two terminals A and B, and because this impedance is infinite, you do not have any current flowing from A to B. So you do not have any current, which means the voltage at A and voltage at B will be equal. And that's what is meant by when we write V minus is equal to V plus, that the voltages at these positive and negative terminals are equal. And that will always be the case if we assume the infinite input impedance scenario. All right. So now, because your I plus is 0, because there is no current going into I plus, the positive terminal, what is the voltage at the V plus terminal? Apply Ohm's law. Exactly. Because at this point, there is zero current flowing. So zero current multiplied with the value of this resistance will be the voltage at this point. That's Ohm's law, right? Voltage equal to current multiplied with resistance. So V plus is also equal to 0, which means that V minus is equal to 0. Keep in mind that we are only talking about AC voltages here. As you see that this is a lowercase v, this is an AC voltage, and we are only analyzing AC voltages at this point. We are not talking about the DC bias. Okay. So when you talk about gain of an amplifier, you are always talking about AC quantities. Okay. So if your V plus is a zero AC quantity, V minus is also AC zero quantity because of the infinite input impedance. So you can find out what is the current IR1, that is the current flowing through this R1 resistance. That would be this Vs voltage minus the voltage at V minus point divided by R1. And because you know V minus is equal to 0, this will be equal to Vs over R1. Okay, so you know that what is the current flowing through this resistance as a function of the voltage at this point and the voltage at this point. Now, because you know that I minus is equal to 0, which means that there cannot be any current flowing into the negative terminal. So there cannot be any current flowing into the negative terminal again. So why would this current go? This current will flow through this resistance, the 20 kilo ohm R2 resistance, right? In an ideal scenario, you would have expected a current division because at this node, there are two different paths, but one path will have a zero current and the other path will have the full current because this path has infinite input impedance. So because I minus is equal to 0, you can write I R2 is equal to I R1. That is, the current through the R2 resistance is equal to the current through the R1 resistance. So now you can readily find out what is your V naught, what is your V output. Your V output is the voltage developed across this V minus point minus I R2 times R2. Again, applying Ohm's law. So the voltage at your output node will be minus of Vs over R1 times R2. So what is the gain? The gain is V naught or V out over Vs. So output voltage divided by input voltage, that is your gain. And output voltage divided by input voltage will be minus of R2 over R1. So you see that there is a negative sign, which means that this is an inverting op-amp configuration. And inverting op-amp only means that if your input voltage looks like a sinusoid like that, the output voltage will be an amplified version of that sinusoid, but also with 180-degree phase difference. That's all it means by having a negative sign at your gain. So this has a gain of -2. And that is your A infinity, because in this calculation, you assume that the op-amp is ideal. And for an ideal op-amp, whatever gain you get is A infinity. So even though the op-amp has had infinite gain, this circuit has a gain of -2. The op-amp had gain of infinity, but the circuit had a gain of -2 because the ratio of this R2 resistance and R1 resistance is just 2. And that's the gain of your overall circuit. You can also find out what is R out, what is R in, and so on. And for that, you'll apply the approach that we have learned in class in the previous few lectures. So let me clean this up a little bit. Okay. So for R out, what you're going to do first is that you're going to set the independent voltage sources equal to be 0 in the entire circuit. What is the independent voltage source here? Vs. So you'll just short Vs when you're trying to find out R out. And then you will apply an arbitrary amount of current or voltage at the output node, and you'll try to measure the other quantity. If you're applying a current, you'll try to measure the voltage. If you're applying a voltage, you'll try to measure the current. That's what you're doing in lab 1 as well, right? And the ratio of that voltage and current will be your output resistance. Now, if you apply as you are applying a voltage at this point, let's say V0, what will happen? There would be a current that will try to flow through this branch. There would be a current which will try to flow through this branch, and there will be a current which will try to go into the op-amp, right? So there are 3 divisions of that current if you're applying a voltage at this node. So let's say you just apply a voltage source at this node, which is Vx, and let's say you're trying to measure the current. So that current will be divided into 3 parts. One will go into this path, one will go into this path, and the other one will flow inside the op-amp. What is there inside the op-amp? You already know about the linear equivalent model of the op-amp, or the AC small signal model of the op-amp. So you have an infinite input impedance. So I can keep the input side open. At the output side, you have a dependent voltage source. And because this is ideal op-amp, the output impedance is also 0. So this is what you have as the model of the op-amp. Now what we are saying that there are 3 currents that are trying to go in 3 different paths. Consider this path that goes inside the op-amp, which is this path. So there will be a current flowing in here. And because this is a voltage source in an ideal scenario will have 0 series resistance. So which means that this current will see a short to the ground. That only means that out of these 3 currents, this current sees a 0 resistance, the current that goes inside the op-amp. That sees a 0 resistance. The other currents will see a finite amount of resistance. As you know that the current will always take the path of least resistance. Where would the current go if you see a 0 resistance? The entire current will go into that 0 resistance path. So there will not be any current division, even though there are 3 possible paths of having the current division. All the current will actually go inside the op-amp, and then it will be drained through this ground node. So what is the output impedance in that case? 0. Because you have a 0 resistance in parallel with the resistance on top and the resistance in bottom. So the overall resistance is still 0. Right? 0 in parallel with a finite resistance equivalently is 0. So the output resistance is 0. You can also put an arbitrary amount of current. So let's say you put a current Ix across V0, and if you do that, you'll see again the same thing, that as you're putting a current source at this point instead of a voltage source, that current has to go somewhere, right? You have a current source over here, and that current needs to go inside the op-amp, which means that it will go through this path, and again it will go to ground through the zero resistance path. So the entire current is going inside the op-amp. It's entirely following a zero resistance path, which again means that the output resistance is zero. Okay. So that's how you find out the output resistance. Question.
Can you explain again why you shorted the dependent source?
Right. So think about any voltage or current sources. So this is from your circuits 1 class. Right? What is a voltage source? A voltage source. So a voltage source will be able to generate a fixed amount of voltage Vs. And what is the resistance associated with it? You have a series resistance with a voltage. If this voltage source is ideal, that series resistance will be equal to 0. Now inside the op-amp, you have this voltage source. Even though it's a dependent voltage source, which means that it's dependent on some other voltage quantity, the value is dependent. But the series resistance, if it is an ideal source, that series resistance is equal to 0. And why that assumption is true here? Because you are assuming an ideal op-amp. An ideal op-amp has output impedance equal to 0 or output resistance equal to 0. And that output resistance is only this output resistance of the voltage source.
So you're still applying just deactivating all sources.
Yeah, first you deactivate all sources. So which means that you deactivate all independent sources. You will not deactivate the dependent source because that's how, like, even in your circuits 1, that's the process you have learned to find out resistances and impedances, right? So why are we deactivating this independent source?
Deactivate. As you said, deactivate all of it.
Right. So here we are not deactivating. What we are saying is that even if you have the voltage source over here, right? What is the, if you are pushing in a current here, what resistance will that current see? It will see 0 resistance. That's all we are saying here, that the output resistance is 0. You are not deactivating the voltage source. Because if you deactivate the voltage source, your output, you will not get any output in that case. Right? Yeah. Mm-hmm.
We had dependent source.
Will that change things? Will that change the
yeah.
In this case, it won't, because at the input side, you have this open. So whatever is happening on the left hand side of it, that will not affect the right hand side. So the current will still flow through this one. All the current will flow through here. So in this case, it won't.
Yeah. I would try to think this scenario that 0 is not R, that where R out equals.
If R out is not equal to 0, you'll only see R out. So that's the resistance you'll see in this part. So what we'll effectively see is the R out in parallel with this R4, which is 4 kilo, in parallel with this resistance, which we'll see this part. So you have 20 kilo in series with 10 kilo. That's 30 kilos. That's what you see in the top part, right? Because this is ground. So 30 kilo is something that you see in the top, through the top path. Through this path, you'll see 4 kilos. And through the op-amp, you'll see a resistance of RO, which is the output resistance of the dependent voltage. Now let's say that RO is 100 ohms. So you'll effectively have 100 ohms in parallel with 4 kilos, in parallel with that 30 kilos. Now you can do that overall calculation, or even if you don't, you can say that it's almost equal to 100, because 100 is much lower than 4 kilo, 100 is much lower than 30 kilo. Okay? So effectively, in that case, the output resistance will be equal to RO. If it is not ideal. More question. For any ideal op-amp, it's always equal. Yeah. But if it is non-ideal, then it could be, it depends on the numbers.
But it doesn't necessarily have R in like percentage
Mhm.
the big thing.
This resistance is 10K, yes.
Yeah, the RA is big.
Yes, yes, that's right. So, I mean, when we go to the next part, I think we are calculating RN as well. Let's see. Yes. So, how to find out RN? So, for that, you'll connect a voltage at the input source at the input side. So, you're connecting your Vx at the input side. What would be your Ix? What would be the current that is going in? You already calculated that. The current that is going in is basically this current, which is going through this R1 resistance. So that would be equal to Vx minus of V minus. So this point's voltage is Vx because you're connecting an arbitrary amount of voltage to find out R in at this point. This point's voltage you already know is equal to 0. V minus is equal to 0. So this point is 0. So what is the Ix current flowing in? Ix current will be Vx minus 0 divided by R1. So Vx over R1, which means your input resistance is equal to R1. And that's the exact quantity mentioned, right? So this is how you calculate your input and output resistances. You connect and you first deactivate all the independent voltage and current sources. And then if you're trying to find out the output resistance, connect an arbitrary amount of voltage source at the output. If you're trying to find out the input resistance, connect an arbitrary amount of voltage source at the input and find out the current. The ratio of voltage to current will give you the resistance. Next, you can find out the loop gain T. For that, you wanted to find out beta. Now, I'll not go through this entire solution because we have looked into these kind of problems, how to find out the beta, how to look at one of the voltage divisions. Just look into it. If you see any issue, just let me know. You can post the questions in the group chat or just email me. But I'm just assuming that you should be able to solve or you should be able to find out beta at this point. Okay, it's just a ratio of, so for example, you can represent this circuit, the linear equivalent circuit, as the one that you see in the bottom, which shows the voltage divisions correctly, and eventually you'll be finding out what is the beta factor. What would be your total loop gain? T will be A times beta. If you know what is A and what is your beta, you should be able to find out what is T. Now, if you know what is T, you can find out what is the loop gain or what is the overall gain when the op amp is non-ideal. And that would be equal to A infinity divided by 1 plus 1 over T. So in this case, you see that the gain becomes about 1.97. In an ideal op amp case, the gain was 2. So as you see that it does not reduce much because even though this is a non-ideal op amp, even though the numbers are non-ideal, that it is mentioned that, okay, you have a loop gain of, or you have a gain of the op amp as 400 and you have this input impedance of 80 kilo ohms and output impedance of 1 kilo ohm, that does not affect your final result by that much amount. Instead of 2, you get 1.97 if you take into account all those non-idealities. So, but that's just because in this case, the input resistance was reasonably high as compared to all other resistance, and the output resistance was reasonably low as compared to all other resistances in the output node. If that condition is not satisfied, let's say this output resistance is 10 kilo ohm instead of 1 kilo ohm, then you'll see a larger difference here. You'll see a larger amount of degradation in the overall gain because of the non-idealities of the op amp. It's only because your input impedance was reasonably high and output impedance was reasonably low, you do not get a lot of effect of the input and output impedances. So similarly, you can look into these other problems where we are again finding out A infinity, finding out beta, and finding out the overall gain. Okay, that's the same 3 steps that we'll follow in each of these problems. So just go through, this is a self-study, just go through all of these problems that are presented here. Let me know if you have any questions. So today we'll be looking into more details of the op amp. All right. So again, as we said, that this is how we expect an op amp to behave. That you have a 3-terminal device, one positive input port, one negative input port, and one output. But of course, in the lab, you'll have to connect it to VDD and VSS. You'll also have to provide the correct biases at the input and even at the output side. So we'll just ignore the DC biasing for now. But when you discuss the internal circuitry of the op-amps, when you discuss MOSFETs, BJTs, we'll go back to this concept of DC biasing again. But in the lab, if you are trying to make an op-amp work, keep in mind you have to apply the DC bias and you have to apply the AC. Right? If you don't apply any one of them, the output will not be as expected. All right. So what's the ideal behavior of the op-amp? The ideal behavior of the op-amp looks like this. If your input voltage is VI, so VI is your input voltage, VO is your output voltage. So at this point you have VO, and VI is basically the difference between these two input voltages. So V plus minus V minus in an AC sense is your input voltage to the op-amp. And how does the op-amps, so let's mark this as VI. The output of the op-amp will look something like this. That as you have a very small input voltage, either positive side or negative side. What does negative input voltage means? It just means that the voltage, the AC voltage at your negative terminal is larger than the AC voltage at your positive terminal. Okay, that's what having a negative. So that's what the left-hand side of this curve means. If you have a small positive or a small negative AC voltage, then your op-amp's output will be linearly, or let me call it this way. So this part is A times VI. So whatever you see in this very small region. So this is a region where you are expecting a linear gain out of the op-amp. So this is the linear gain region, but then the gains saturates at high values of input, whichever it is. It may be on the positive side or on the negative side. If the value of the input is high, the output will saturate to some value. Why? Because of course, imagine this case that your op-amp has an infinite gain, ideally. If you're applying, let's say, a 1 volt input to it, your output should be infinite. But can you get infinite voltage at the output? No, right? You cannot get that from a real device. What will happen at the real device is that the output will be clipped at 2 levels. It could be a positive level and a negative level. In most cases, it will be VDD and VSS. So this could be equal to your VDD and this could be equal to your VSS. Because in any electronic circuit, you cannot create a voltage which is higher than VDD. You cannot create, in fact, you cannot create a DC voltage which is higher than VDD. And you cannot create the DC voltage which is lower than VSS. In certain scenarios, you can create an AC voltage which is higher than VDD, but again, we'll not go into those details. So let's just assume that, okay, you have your VDD and VSS, those are the 2 levels where this signal is getting clipped to. And the clipping part is obvious, right? It is clear to you. Why does it clip? Because you cannot create infinite voltages, or you cannot create very high voltages, or any voltage that is higher than VDD, or any voltage that is lower than VSS. That's why you see the clipping phenomenon. Now, if you apply a negative feedback to the op-amp, what happens? Let's just assume that you take the voltage at the output, you provide it back to the negative input. And let's say you have a positive VI at the positive input side, right? So what's VI? That is the difference between your positive input and negative input. That difference is something that you are connecting back at the V0 side, connecting back at the output side, right? So what we are drawing here are 2 plots. One, as you are applying the input, as you are applying a positive VI, how would your output look like? And the first question is, why does the direction of the output change here? So in the previous case, as you apply a positive VI, you saw that your output was a high positive value. And as you apply a negative VI, the output was a high negative value. In this case, why is it different? Why is it a high negative value if you have a positive VI, and high negative value when you have a positive VI, and a high positive value when you have a negative VI. Why did this plot get inverted? That's because in this case, you were defining the input as the voltage between the positive terminal and the negative terminal. Right? In this case, your negative voltage is here, the positive voltage is here. It's just that these two terminals have reversed the way we are drawing the op amp and the way we are defining VI. Right? Your negative is on top and positive is at the bottom. In this case, it was the opposite. It was plus and minus. In this case, it is minus and plus. And that's the only reason why you are seeing this inversion. Okay. So that's one thing. The other thing is that what is the expected output that you have here? Because the output is connected back at the input, we are drawing this line, which is your output is equal to input line. So the op amp's behavior is something like this. This is the expected behavior from the op amp. But because you have a feedback connected, the expected value at the output should be exactly equal to the expected value at the input because they are shorted together. So the final solution to this is basically this point where both of these curves intersect. So you satisfy the equation that your output is equal to input, and you also satisfy the behavior of the op amp. So that is true only at one point where your output is equal to input. So when you have a negative feedback like this, it's called a unity gain negative feedback. That you have your input applied between the positive and negative terminal, and you connect your output back to the negative input. This is called a unity gain negative feedback. And in this case, the gain of the op amp or gain of the entire circuit is equal to 1. So this is the graphical representation why it is equal to 1, because your output is equal to input because of the direct connection. So even if the op amp ideally has infinite gain, the gain of the total system when you have this feedback connected will be equal to 1. And something that you have learned in the problem that we discussed earlier in the lecture, here as well you are doing the same thing. You are applying the input at the negative terminal, and the output was fed back into the input side with a 20 kilo ohm resistance, right? So only difference was that there were these two resistances of 20 kilo ohm and 10 kilo ohm that were connected. One was connected between your application of your input voltage and the negative terminal. The other one was connected between the negative terminal and the output. And in this case, you found out what is your gain, what is your A infinity. It was minus R2 over R1. What if this R2 and R1 are equal? If R2 and R1 are equal, you get that unity gain. Instead of 2, you get a gain of equal to 1. That's the same thing we are showing here. That because there are no resistances, it's basically the equal amount of resistance at the input and output side. If you're not physically connecting any resistance. So that ratio of R2 over R1 becomes 1, and that becomes a negative feedback. So you can, a unity gain feedback. So you can prove this mathematically as well, just by doing an analysis like the previous example. Question? Yes, so the previous one was not a definition. So 1 plus R2 over R1 or minus R2 over R1, these are not definitions. Right? This is the solution of the circuit. You solve the circuit, you applied KCL and KVL, and then you found out what is A infinity. This is not the definition of A infinity. Definition of A infinity is the gain of the system when your op amp is ideal. That's it. It does not talk about R2 or there could be 50 resistances in the circuit. Would it still be R2 over R1? No. Right? So this is something you find out as the circuit or how the circuit looks like changes. So you can connect maybe 2 more resistances over here at any point, and then your A infinity will change. Yeah. More questions? Yeah, negative feedback in this case. Yeah. Yes, yes.
So then why on the other side does it want?
Or in the previous problem. In the previous problem, you connected, so,
I get that it is one, but like that also very common.
oh, on this one, right? Oh, so yes, I should clarify this. So this is -1, which means that you already see this inversion, right? That your input, if your input is positive, your output is negative. If your input is negative, output is positive. So that inversion is already there. But what I was saying is that the magnitude of the gain is equal to 1, but of course you'll have this negative sign as well. So it is -1. It's better to say that the well, no, not really. Sorry, I take it back. In this case, it is equal to +1 because where are you applying your input? You're applying your input at the positive terminal. You're not applying your input at the negative terminal. So there's a slight difference. It's a non-inverting op-amp. So non-inverting op-amp was something that we discussed in the previous class. If you go back to the previous lecture, we had non-inverting op-amps, and for non-inverting op-amp, the gain equation was 1 plus R2 over R1. Yes.
Call it negative feedback because
Because you're feeding back the output at the negative terminal. So let's say you're feeding back some amount of output at the negative terminal, right? If you're, and what does the effective input become in that case? That is the voltage at this point minus the voltage at this point, right? If your output voltage increases, this point's voltage will increase, and the overall voltage that you see in the input side, in that case, will decrease. That's why you are calling it a negative feedback. Also, as you said, that you're feeding it back in the negative terminal. That's the reason why you call it a negative feedback. If you feed it back in the positive terminal, it becomes a positive feedback.
and the positive feedback, I guess, like many of the equations we have learned.
Yeah. So we can go back to the lecture on feedbacks. So for negative feedback, this was your equation. This was your feed forward path. This is feedback path. And what does negative feedback look like? That you have your input here at the positive terminal. Your feedback is at the negative terminal. And in this case, the equation is A divided by 1 plus A beta. That's your overall gain equation from your input node to the output node. If this were a positive feedback instead of negative feedback, this would have become 1 minus A beta. So that's the inversion that you're talking about. More questions? Yeah.
Clarify this of the operating.
The operating point is the biasing point, or the DC point, or the quiescent point. So right now we are completely ignoring. Why are we ignoring? Because we are only trying to see what is the AC gain of the op-amp, or we are trying to analyze the AC gain of the op-amp. But the operating point or the biasing point is the DC point where what you need to apply to make sure that the op-amp has gain. It's just as we talked about the steam engine, right? That you need to bring it up to a temperature where water can become steam. If it is at room temperature, it will not become steam. So if you're putting in water and you are expecting steam out of it, it will not happen at room temperature. That's the analogy of having a DC biasing point or an operating point. More questions? Yeah.
For that diagram right there, that basically points to that the source is going to be the positive of the op-amp.
Yes.
Feedback is negative.
Yes. All right. So actually, what you were just asking, we are explaining in the next part is with the feedback block diagram. That okay, you have your feed forward gain as A, your feedback gain is B or beta, and then you're putting it back at the negative terminal. And you solve this, you come up with this equation that I have mentioned on the board, and we had solved it during, I think, lecture number 4. So that's your overall gain equation with the feedback. Even if this A could have been infinite, if this A is an ideal op-amp, then the value of A is equal to infinite. But the overall gain of the system is not infinite. Now you can represent this as 1 over 1 upon A plus B if you are dividing the numerator and denominator by A. And if you are dividing the numerator and denominator by A times B, you come up with this equation. Now this is something you have already looked into in some other form, that AB is equal to the loop gain, right? So that is equal to T. And 1 over beta is basically your A infinity. That's again something we had discussed when we were learning about feedback, that why A infinity is equal to 1 over beta. And that is evident from this equation as well. That what is A infinity? That you assume your original gain of the op-amp is equal to infinity. That means this A is equal to infinity. So how would you represent the gain of the system when the A term is equal to infinity? So you'll have an infinity in the numerator, in the denominator you also have some infinity terms, so you cannot define it properly. So you divide the numerator and denominator by A, and you come up with this equation. So your numerator is 1, your denominator is 1 upon A. If A is equal to infinity, then this term goes away. What you are left with is just B. Right? So this is 1 upon beta or 1 upon B is basically your A infinity. So this is another way of showing that we are working with the same equation. Even though we are representing them in different forms, we are working with the same equations. Yes. So A infinity does not mean infinite gain for the overall system. A infinity means I think we can change the notation a little bit. But what it means, think about the A infinity that we learned about in the previous class. What is that A infinity? It's the gain of the system when the op-amp has infinite. When the feed-forward path has an infinite gain. And this confusion can arise because we always define the gain of a system as A, amplification, right? So what we are saying here is that if this is infinite, then the overall gain of the system will be called as A infinity. And A infinity is equal to 1 upon B or 1 upon beta. Okay. Does that answer your question, right? Yeah. All right. So this was the example that again we have been looking into for a few lectures, and this is the non-inverting op-amp configuration. Why non-inverting op-amp? Because you're applying your input to the non-inverting terminal of the op-amp, to the positive terminal of the op-amp, and you have your feedback connected between the output and the negative terminal. So it's a non-inverting op-amp configuration, but as you had pointed out, this is also a negative feedback configuration. So there are multiple things going on here. It's a non-inverting op-amp configuration, but this is also a negative feedback configuration because you're applying your feedback to the negative terminal. And you can solve this by drawing the linear equivalent model of the op-amp, and you can apply your nodal analysis, and then you come up with this equation eventually, that your A infinity will be equal to 1 plus R2 over R1. So your A infinity, which is assuming an infinite gain for the op-amp, the overall gain of the system will be 1 plus R2 over R1. So again, coming back to the question that you asked, that A infinity is not a definition. A infinity is the gain of the system when the feed-forward path has an infinite gain. The equation can change depending on the circuit. For the non-inverting op-amp configuration, the equation for A infinity is 1 plus R2 over R1. For the inverting op-amp configuration, which we had seen earlier in the class, A infinity is equal to minus R2 over R1. And the overall gain of the system that you can call as a closed loop. ACL represents a closed loop, which is the closed loop gain of the system. Right? So when you have a feedback loop, what is the overall gain of the system in a closed loop scenario? That is basically A infinity divided by 1 plus 1 over T. Okay. Question? A infinity is same as, no, A infinity is gain of the system, assuming that you have infinite feed forward gain. The open loop gain is defined in a different way. So electronic circuit is sometimes more about the nomenclature. So what open loop gain means is basically what is your loop gain, what we have been defining as loop gain, that T. This is your open loop gain. So A multiplied with beta, that's called open loop gain. A infinity divided by 1 plus 1 over T, that's called closed loop gain. A itself is called the feed forward gain. If that feed forward gain is infinite, then the gain of the overall system is equal to A infinity. Okay, so let me write that down just so that we are not missing anything. So let's get this nomenclature cleared out. A is called the feed forward gain. Beta or B is called the feedback gain. A times beta is the loop gain, or in some books you'll find this is being called as open loop gain. Why open loop? Because yes, if you have both A and beta in your signal path, but you don't connect it back, you don't actually, if you don't close the loop, then it's called open loop. And that's why A multiplied by beta is called a loop gain or an open loop gain. So that can also be represented as something like AOL, which says A open loop. So in some books, you'll see it is written as AOL. And A closed loop is the closed loop gain. That, and before going there, maybe let's define A infinity. Or maybe we can also do it the other way. So A closed loop is equal to A infinity divided by 1 plus 1 over A open. And your open loop gain is also in, again, many different books follow different nomenclature. I'm just putting everything together here so that if you're referring to different books, you don't get confused with what we are talking about. So open loop gain is same as T, that is your loop gain, that is equal to A times beta. Feedback gain and feed forward gain are, I think, very clear at this point. Closed loop gain is basically A infinity divided by 1 plus 1 over A open loop gain, which is basically equal to T. So what is A infinity? A infinity is the value of the closed loop gain when your open loop gain is infinite. And when your open loop gain will be infinite, because beta is always less than 1, it will only be infinite when A is equal to infinite. So when A is equal to infinite, the overall system's gain will be called A. All right. So that was your non-inverting op-amp and the way we were defining all the different terms here. Now, I think it's already time, so we'll take it from this point, and in the next lecture we'll talk more about inverting op-amp and other configurations. But always keep in mind that this is how we're defining the nomenclature. So keep this in mind and try to link it back to whenever we talk about loop gain, open loop gain, closed loop gain, A infinity, T. What does each one of those terms mean? Just be very clear about each one of them when you are solving the problems or solving the homework. Yeah.
So this is for negative feedback, right?
Yeah, thank you for. Yeah, thanks.
Right now,
Yeah, yeah,
divided by one.
yeah. So this is for negative, not for positive.
So I have found something.
Yeah.
So when you have the negative feedback, when T increases, if the T increases, it pays more like an idea of.
When the T increases, it gets more like an ideal order. Yes, yes. Because what does T increase mean? That A is increasing, that it becomes more like an ideal order.
Good. And now, Eric goes,
But if you have a positive feedback, then as T increases, still you will have the same thing. You have one plus a very large quantity, a very small quantity, because one upon a very large quantity is small quantity. Or you have one minus a very small quantity. Does not matter.
if we had like the T constant, and we had to compare the negative and positive different ones.
Yeah.
I would see that in this one is plus, so if the T, well, the T is made for this, let's say. Be, like, have the
Yeah.
game,
Yeah, this right
Yeah.
example what you were talking about, that if your this T right this, so if your T increases, the center term reduces, which means that one plus this will reduce, right? So your overall gain will increase. So if your T increases, or let's say when T is equal to 100 or 200, it's not impact. If T increases, this reduces, which means this is also.
but with the other one, with the.
With the other one, if it is minus, then as T increases, this part reduces. So one minus something that is reduced, so that means this will increase and that will increase.
Yeah,
So this is with negative feedback and this is with positive feedback.
That's what I would.
But if I had the T the same, if I change it again to increase.
Yeah.
Change it to positive feedback, and then the negative feedback would decrease.
That's a very interesting turnovers that happens.
Ah,
This is very interesting, but thanks for pointing this out. Yes.
We have some question.
Yes.
So, that we define. We're asking for 80, so you have, and.
It's a current, yeah. I think someone asked the question of Murthy and we also replied that, yeah, no. So what is AC? A is the voltage gain of your op amp. Let's say you have your input voltage, that is V in, and V out. AV of the op amp just means that V naught over V in, and that is probably defined as maybe 500. So this is fine, but this op amp is connected in a configuration, and I'll be talking about the current amplifier configuration. I wanted to do that today, but there was no time. But in next lecture, I talk about how this op amp can be configured in a current amplifier configuration, and we already have that. We can look into the today's lecture. So if you go back to
It's on the notes.
it's on the notes. If you look into op amp intro, you'll find this one. So after inverting and non-inverting amplifiers, there are a few exercises, but then I think I'm talking about. Maybe not here. So I'll upload this. And then what we're talking about, and I'll call it reference document to solve homework 2, problem number 3. Okay. So that you know how to use the op amp in a current amplifier configuration, even though the op amp has a voltage. So I think that will solve your question.
So, both will use how open loop gain involves data, because when you think open loop, you think no feedback.
No, it does not mean no feedback. So again, it's about nomenclature. Then let's say you or I can think about the fact that okay, open loop means no feedback, but that's not how the electronic circuit community defines. The electronic circuit community defines open loop as a condition, because otherwise, why would call it a loop? Open loop means a loop is present, but you are not connecting the loop. You're keeping it open loop. So it means that you have a gain of A and gain of B, representation of the feed forward gain and the feedback gain, we call that an open loop. That's a matter of nomenclature again, like how you define the open loop.
So if you like took this route, you just had this, D would be one.
D would be one.
Okay.
So that's how we define the open loop function. And you have a loop, but that loop is open.
So
And
then,
closed loop
how
means
do you
you have. How do you?
like, so how do you get to this? Like from, like, so A beta is,
A times beta is the open loop gain or T.
okay,
So we already saw this, right? So when you have A here and beta here, and you connect it back, connect it in a negative feedback, so this is plus, this is minus. Then your DO over DS, that would be equal to A divided by 1 plus A beta. Okay. You just solve the KCL and KVL, you'll get to this.
okay.
And that's something we did like
Yeah,
in the class, right?
I know we've done.
Yeah. So A divided by 1 plus A beta, that's your overall gain of the system.
Okay.
Now you divide your numerator and denominator both by A beta. So what do you have in the numerator? You have 1 upon beta. What do you have in the denominator? You have 1 upon A beta plus 1. And that's what we are writing here. It's the same equation. It's just that because there are so many different terms involved, it may look a little confusing in the beginning. But if you work out a few problems, it will be very clear. That your 1 upon beta is A infinity. Right? Your 1 upon beta is exactly equal to A infinity. Your A times beta is equal to this.
Yeah.
So these two are the same equation. So all of them are the same equation.
Okay.
It's not a different equation, it's the same equation, but in some cases, and how do you get to the fact that A infinity is 1 upon beta? You divide the numerator and denominator by 2. So you get 1 divided by 1 upon A plus beta.
Okay, I just need to go back over this here.
Yeah.
Okay, all right.
So then it will be very clear. Right? But and just so that you know, all of them are talking about the same equation. It's not a different equation.
Okay, thank you.
Yeah, that's all. That's subject.
Okay.
Your patrons.
If students do not have a problem with that day, then it will not, it will be the same as it is. And I definitely want it to be before the final week, actual final week, because in the final week you have other exams, and also it will become very hard for the teachers to grade on the, if it is on the final week, grading 100 students is very difficult. So December 4th works for you.
Yeah.
I not like to change the December 4th deadline or date as much as possible.
I think it's a really fun on this, so yeah, you can disregard all that.
Okay, I'm sorry, I had a deadline yesterday, I was not able to reply. But yeah, I remember that you had sent an email. I just replied.
Oh,
Okay. I don't know, maybe it's short. So we get into this side. That always, we are not shorting. Everyone shorting it because that's the process. That's the approach that you can take, that you short all the independent quotation. But when looking into the occurrence, if the occurrence is ideal, we'll see a zero rates. If it is non-ideal, we'll see a relation of RO within the output rates. That's for non-ideal. When you look at the occurrence, we'll see a relation of RO within the output rates. If it is ideal, we'll see. So that's all we are saying here. That here, and we understand this. Why we use it? Because you're seeing the voltage on the system. The resistance of voltage is you don't need to short it.